So I'll share with you our experience with the trifocals. Since this is a new technology, we took a little bit of time to understand what was going on and what the company jargon meant, and I'll try to share a little bit of that background with you before I proceed to my actual presentation. So evolutions of multifocals have gone through multiple steps, and why did they keep looking for a better solution is because they wanted improved intermediate vision, and this was without reducing the near and far vision. So diffractive multifocal lenses are kind of the order of the day, and in diffractives, basically some amount of the energy is spread over the multiple foci that are present based on the diffractive structure. There is constructive interference, and the constructive interference is what creates the two main foci. The far vision is from the zero order of the constructive interference. The near vision is first order. The other orders go towards creating the dysphotopsias. Destructive interference, when it is more, is what is associated with the loss of contrast. So that is the physics behind it. And depending on how you create the steps and give the height of the steps, there is it's almost inevitable that the lens can only do so many things. So you can have a near and distance equal balance, and you cannot really increase beyond it's 80-81% light recruitment for useful vision. The other foci are lost vision or contribute to the dysphotopsias. So the diffractive steps, the IOL curvature is what determines the far power. The diffractive grating is providing the addition. The zero order is devoted to distance focus. The first order is for the near focus. And all higher orders are contributing to either loss of contrast or towards halos. So the diffractive step, the width of the step is what determines the add power. The smaller the step, the higher the power. The larger the step, the smaller the power. The step height determines the energy distribution between far and near, and companies manipulate it for specific purposes. The higher the step, the higher the quantity of energy for near vision. Smaller the step, the higher the quantity for distance vision. A constant height over the entire surface means it becomes pupil independent, and when you decrease the step height from center to the periphery, you have a greater distance in the center and greater near vision in the center, and reduction as the pupil dilates, which is useful for night vision, and this is what is called as apodization. So the combination of two diffractive structures is what trifocals is all about. There is one with smaller step width, which is higher power, 3.5 for the fine vision and 3.33 for the Zeiss 80 Lisa. And the second is a fraction of that, half typically, which is 1.75 or 1.66. And the combination of these two gives in the fine vision intermediate vision for 1.75 and near vision for 3.5, and the Zeiss trifocal 1.66 for intermediate and 3.33 for this near vision. So how does this work? The first order structure is the 3.5 near vision add, 0 goes for far vision, the first order goes for the 3.5 near vision. Additional beyond that is lost light, halos, or contrast loss. The second diffractive structure contributes to far vision. The 1.75 or the 1.66 contributes to the intermediate vision, and the multiple of that is used to contribute to the near vision. And this recruitment of the second order diffractive structure for near vision is what improves the photic phenomenon in these eyes, and also gives the better near vision. So the trifocals, basically the total energy lost is reduced, and the diffractive structure is pupil dependent, allocating more energy for far in dim conditions. So the trifocal which we have used is a preloaded trifocal, 6 mm biconvex on a plate haptic hydrophobic surface with diffractive rings covering the entire optic. The central 3.34 millimeter is trifocal, the rest is bifocal up to 6 millimeters, and it's a aspheric design with a Q value of minus 0.18. This is how they came to the LISA thing. The light intensity is distributed asymmetrically. The optic acts independent of pupil size. There is a little rounding of the steps to reduce the photic phenomenon again, and it's aberration correcting. So what we have done is the preliminary assessment of 21 eyes of 13 patients, average age of 52. Average uncorrected pre-op was about 3/60, best corrected was 6/30. And on the first post-operative day, they all did quite well, 6/6. Uncorrected near was 20 centimeters was N6. Uncorrected intermediate at 80 centimeters was N10. The vision on 14th, and so what vision you get on the early days was actually more or less what you get at intermediate and 6 weeks also. And there is no change between the 14th and 6 weeks, 2 weeks and 6 weeks. Uncorrected remains 6/6, N6 and N8. So the binocular defocus in these patients does not show a significant dip in the center there. Plano and with minus, the add kicks in, but the dip, which is common with the typical multifocals over here, this is not seen, and the intermediate is much more closer to 0. So this is associated with reduction in glare halos and photic phenomenon, some improvement in the intermediate vision. And to conclude, what I would say is it gives very good uncorrected distance and near vision when your biometry, etc., surgical technique is perfect. It gives a somewhat improved intermediate vision without compromising the near vision. The contrast reduction has never been an issue with any of these patients. The photic phenomenon, I would say the percentage that experience photic phenomenon compared to the traditional multifocals is about the same. But since the amount of brightness of those photic phenomenon is much lesser, they don't find it so bothersome. And so in my case, at least, it has reduced the headache when I have an unhappy patient post-operative. Thank you.